Well, hello everyone, and welcome to Colloid and Surface Chemistry lecture number 5. So in this session, I would like to recap on surfactant systems and go back over some of the theory that was introduced in the last session. And importantly, I want to consider different ways in which we can measure that critical micelle concentration that we spoke about last time for surfactant systems. I also want to consider why we need to know the critical micelle concentration. So hopefully I'll give you some examples of where knowing the critical micelle concentration is important, and consider some of the applications in which micellar aggregates are used. So a very quick recap on some of the surfactant theory that we studied in the last lecture then. We know that on the surface of water, molecules that reside on the interface are subjected to unequal short-range attractive forces. They're not surrounded by the same number of water molecules that they are in the bulk solution, and because of that, they feel a net inward pull into the bulk phase. The molecules on the surface then are a slightly increased energy, and that is fundamentally the origin of the surface tension in water, and we describe it as the surface free energy. And I think that slide describes exactly what I described on the previous page. What happens then is that the surface with its increased free energy contracts because it aims to minimize the area that is in contact with the gas phase, because that's more energetically favorable. And this results in something we call the surface free energy. It's a surface free energy per unit area of the interface or the surface, and this again is surface tension. It's measured in millinewtons per meter. We spoke last time about the fact that surfactant molecules adsorb to the interface. They adsorb to the surface of water, and when they do that, they significantly reduce the surface tension of water. And we know that they adsorb to the interface. The driving force from a thermodynamic perspective for their adsorption to the surface then is unfavorable hydrophobic interactions with the bulk phase. So what we're essentially saying is surfactant molecules do not want to be in the bulk phase, because those long hydrocarbon tails that extend away from that head group don't want to be in contact with the water phase. When they're present on the surface of the water here, that is a favorable process, because the head groups, which we said last time are hydrophilic and are often charged species, are perfectly happy to reside in the bulk water phase. And those long hydrocarbon tails then extend away from the water interface, because again, they don't want to be in the water. And again, we looked at this from a thermodynamic perspective last time. That migration of surfactant molecules from the bulk phase to the interface is a thermodynamically favorable and spontaneous process. Now, at some point, you're going to run out of space on the surface of water, right? You're not going to have any more room to pack water molecules. To pack surfactant molecules. So the question then is, what is the most thermodynamically favorable way for surfactant molecules to aggregate into much larger structures? And when you reach this limiting concentration at the interface, when you can't pack any more surfactant molecules on the surface, the surfactant molecules start to aggregate into structures that we call micelles. The concentration at which they do this is known as the critical micelle concentration. So at this critical micelle concentration then, the interface is at its maximum in terms of the number of surfactant molecules that you can pack on the surface. And in order to minimize the free energy of the system, that is, in order to ensure that those long hydrocarbon tails of surfactants, which now must reside in the bulk water phase, aren't in contact with the bulk water phase, surfactants aggregate into these structures that we call micelles, where in the core of the micelle, all of those hydrophobic tails are able to interact in that hydrophobic environment, and it leaves the head groups pointing out towards solution. And we can measure this by looking at the surface tension of the liquid. And as we increase the surface tension of the liquid, as we increase the concentration of surfactant molecules, the surface tension of the liquid starts to decrease, and it decreases as we increase the concentration of surfactant molecules on the surface. Up until that point at which we saturate the surface with surfactant molecules and we can no longer pack any more surfactant molecules at the interface, in which case we see a plateau in surface tension. You could also plot that as a function of the amount of surfactant that's absorbed at the interface versus concentration. It's exactly the same plot. Now, one question is, well, why do we need to know the critical micelle concentration? You might say to me, what's the point in measuring the critical micelle concentration? Well, it has some massively important industrial implications. So surfactant molecules are the foundation of any detergent that we use in the home. Now that could be from soaps through to the detergent that you put into your washing machine to clean your laundry, or your dishwasher to clean your plates, or indeed the fairy liquid or washing up liquid that you use to clean plates after dinner. It's important in soap formulations that we have surfactant molecules above the critical micelle concentration, so we have micelles in solution. And that's because the actual cleansing action of soap is such that any grease that you find, let's take washing up after dinner as a prime example here. On your plate, let's say you've had beans on toast for dinner. On your plate is grease that is difficult to rinse off. If you scrubbed that with just a clean cloth, you can imagine that it would be really difficult to get rid of the grease that's on your plate or your roasting tin. All of you will know that when you add some washing up liquid to that system, suddenly the grease becomes much easier to rub off with a cloth. What's happening on a molecular scale there is that the surfactant molecules, which are above the critical micelle concentration in this micellar state, are actually allowing the incorporation of grease into the micelle and solubilizing the grease. If you think about, roasting a chicken or cooking a beef burger in a pan, it creates a lot of fat and grease. That fat and grease is itself hydrophobic and it doesn't want to be in the water phase. That's why it's so difficult to scrub once you've cooked with it. If you include a surfactant system which is above the critical micelle concentration, then grease can be incorporated into the core of those micelles, into that hydrophobic environment where all of those long chain carbon molecules are, and suddenly you solubilize grease and it becomes a lot easier then to scrub your plates clean. So that's one of the reasons why, from an industrial perspective, it's very important that we understand where the critical micelle concentration is and how we can use that to formulate the industrial products, which are domestic products, which are used in home formulations, home care formulations. That also holds for shampoo and any other personal care formulation that you might come across. Now, I show you here some titles for some academic journal articles. And this is a really important and emerging field within colloid and interface science, and it's the application of micellar structures to drug delivery. And it's picking up a lot of pace in the pharmaceutical industry now. A lot of pharmaceutical companies are looking at micellar structures for the delivery of drugs. It's very easy to incorporate a drug that isn't soluble in water inside a micelle. And you can then use that drug in an aqueous formulation to deliver to a patient, whether that be through a drip or some kind of transdermal injection. So the first thing is that you can very easily incorporate a hydrophobic drug into an aqueous formulation. Secondly, you can think about controlling the release of the drug. So if you have a drug in a micelle system, it might be that the body metabolizes that drug in a very different way to how it would metabolize the free drug in the bloodstream or in the gut or wherever. And it might be that your drug molecule diffuses very slowly out of your micelle. So you can have a controlled and sustained release of a drug from the core of a micelle. Now, think about the logistics of formulating that kind of drug suspension. You need to have a solid understanding of the critical micelle concentration of the surfactant that makes up the micelle before you can think about incorporating a drug and controlling its release. Now, this says exactly what I've said on the previous slide. A lot of the modern applications of micellar structures in the recent literature tend to be very much focused on pharmaceutical applications. So again, we can incorporate drugs into the middle of the micelle. We can change the molecular architecture of the micelle to influence the diffusion properties of the drug. We can slow diffusion out of the micelle or increase diffusion of the drug out of the micelle. You can functionalize the surface of the micellar aggregate with molecules that make it less susceptible to attack from the host immune system. You can create stealth nanocarriers that are able to carry a drug through the circulatory system unhindered by any potential impacts of the host's immune system. And you can even think about targeted drug delivery. You can functionalize the surface of the micellar aggregate with molecules that will bind with a certain biomarker, for example, something that resides on the site of a tumor. So you can ensure an increased delivery of your drug to the site of a tumor, for example. Now, this raises the question, if the critical knowledge of the critical micelle concentration is so important, then how can we think about ways of measuring the critical micelle concentration? And this is a very critical question to address in colloid and surface science. And there are a number of ways. There are three key ways that we can measure the critical micelle concentration. You will be doing one of these in the laboratory in a few weeks' time. The first is surface tensiometry, so we can track the surface tension as we increase the concentration of surfactant. The second is to use conductivity measurements, and we'll talk about that in a moment. And the final are fluorescence methods. Very simply then, surface tensiometry involves measuring the surface tension of water in the presence of your surfactants at increasing concentrations until you observe that plateau in surface tension. The concentration at which that plateau ensues is the critical micelle concentration. What you use is something called a surface tensiometer with a Dunois ring or a Wilhelmi plate. And what that does is it draws, you can see on the left-hand image there, it's something we call a Dunois ring. You would immerse the Dunois ring in the water phase and drag it up through the water interface and measure the force that is required for that Dunois ring to break with the water interface. The force that takes is equal to the surface tension in millinewtons per meter. So there we go. You've got a force that acts on that ring as it is withdrawn from the liquid phase, and that's used to measure the surface tension. And there will be a maximum force that occurs when the ring moves through that air-liquid interface, and you can correlate that to the surface tension. All you need to know is the sum of the inner and outer circumference of your Dunois ring, and you can work out the surface tension. Similarly, you can use something called a Wilhelmy plate, and it operates in exactly the same way. It's just that the calculation of the surface tension is slightly different. What you gain then is a plot of surface tension against surfactant concentration, and you would take measurements over an entire concentration series in order to work out where that critical micelle concentration occurs. You can see that initially there is a linear dependency on the logarithm of the surfactant concentration. And as you increase the surfactant concentration, the surface tension goes down until it starts to plateau. And that plateau point is the critical micelle concentration. Modern surface tensiometers make things very easy because they are all automatic. So you would set up a stock solution of your surfactant, and it would inject small concentrations, small volumes of that into your measurement vial, and it would automatically dose and increase the concentration of surfactant and take measurements after each dosing. And that gives us a very accurate determination of the critical micelle concentration. You can also use conductivity as a method of working out the critical micelle concentration. You use a conductivity meter here, and the conductivity meter measures the potential between two electrodes, and it calculates the conductivity of that solution, and that's based on the number of charge carriers in solution. So the higher the number of charge carriers, the higher the conductivity. Now, if you think about a charged surfactant, some of for example, the anionic surfactants that we looked at last time, such as the sulfonates or the sulfates, the outside of the micelle is composed of surfactant head groups, so charged head groups. Surfactants are also charged. What you get then is a plot of conductivity versus concentration. And overall, the addition of more surfactant yields an increase in conductivity. That's because when we're talking about a charged surfactant, we are increasing the number of charge carriers in solution. But you'll note in that graph there that there's a distinct change in gradient, and this is the most important point. Initially, before the critical micelle concentration, all we're doing is adding monomeric surfactants to the solution. They're not aggregating into micellar structures yet. So the rate of conductivity is change with concentration is quite high. You'll note that rate slows down when we reach the critical micelle concentration. And that's because after the critical micelle concentration, when these surfactants aggregate into micellar structures, they're much larger. We've now got very big micelles in solution, and they're not as efficient as at carrying charge. They diffuse much more slowly through solution, and therefore the conductivity appears lower. So it's that break-in gradient that you see that we assign as the critical micelle concentration. And this is the experiment that you're going to be doing in the laboratory in a couple of weeks' time. So again, above this CMC, we've got much larger aggregates in solution, these micellar structures. These diffuse more slowly through solution, and the rate of conductivity changes. You can also use fluorescence methods, and you've got to use a dye that is sensitive to its environment, i.e. it fluoresces under some kind of environment change. This fluorescence dye here is called THP1, and under excitation it will emit light when it's in an aqueous environment. So if it's in solution, it will emit light. If it is in a hydrophobic environment, then emission is quenched. So you don't see any fluorescence from the dye if it's in a hydrophobic environment. Now, below the critical micelle concentration, that dye is in an aqueous environment. Therefore, when you irradiate a sample, you see a very high fluorescence intensity. But upon micellization, that dye, which would rather be in a hydrophobic environment, starts to preferentially aggregate in the core of the micelle. Now that dye is in a hydrophobic environment, and you see a very large decrease in fluorescence emission. And you can see that on the graph here. This is taken from a paper, the reference I give you in the bottom left there. You gain an initial increase in fluorescence as the dye starts to aggregate in solution. But then upon micellization, you see this rapid decrease in fluorescence as the dye is incorporated into the hydrophobic core of the micelles. That point at which fluorescence decreases is the critical micelle concentration. And you can see there that there are a few more graphs there taken from this paper. Now think about the material over the last two lectures and try and relate the theory here to laboratory 1. So I'd really like you to spend the remaining time for your asynchronous online study this week to relate the surfactant theory that we've covered over the last two lectures to the first laboratory in this module, all of which are on the Moodle space.